This video demonstrates the pilot scenario 1.5, which showcases how ELECTRON detects Modbus TCP denial of service attacks in a sandbox environment. In the realm of cybersecurity software development, having a flexible and secure virtual sandbox is of paramount importance. Through a virtual sandbox, complex and realistic topologies can be replicated, allowing cybersecurity technology providers to test their products in realistic environments without compromising the security of the production environment. At the same time, end users can observe how the cybersecurity tools operate in realistic network environments, and can also be trained on efficiently managing and configuring those tools. Moreover, through virtualization, the scale of the virtual environments can be increased accordingly, given that the specialized OT systems can be emulated in the virtualized environment. In this scenario, the validation of the ELECTRON platform is performed in a sandbox environment, provided by GNS3. The scenario involves the detection and mitigation of Modbus TCP denial of service attacks, all happening in the GNS3 sandbox environment. This is a summary of the components that comprise this simulation. The environment aims to replicate a Modbus-based energy meter reading infrastructure, which can be found in the supervisory control and data acquisition systems of thermal power plants. A custom-made Docker image was created, which leverages the PyModbus Python library, in order to simulate a Modbus TCP energy meter. The simulated energy meter responds to Modbus TCP commands as a real Modbus energy meter would do. Through the Docker engine of GNS3, several instances of the virtual energy meter were deployed, in a resource-efficient manner. Then, Ubuntu-based virtual machines were created, in order to replicate the advanced meter reading head-end, and the attacker. The AMR head-end periodically retrieves and visualizes the measurements of the Modbus energy meters. Moreover, the attacker is another Ubuntu VM, which uses the Modbus penetration testing tool, customized by the University of Western Macedonia, in order to conduct the Modbus denial of service attack. According to this attack, the attacker aims to flood the targeted energy meter with write single register commands, rendering the meter unresponsive. Finally, Open vSwitch containers are utilized to represent the SDN switches. This is the sandbox environment in GNS3, developed for this scenario. The purple subnet represents the Modbus-based OT network, and is completely isolated from other networks. The blue subnet represents the management network, and has access to the Internet. The ELECTRON SDN controller and dashboard connects to the management interface of the SDN switches, through a typical Layer 2 switch, and via the management network, according to the out-of-band management approach. The Federated Learning Intrusion Detection System, or FLIDPS, is connected to both networks. The interface on the OT network is used for getting mirrored network traffic, through port mirroring, which enables real-time detection. The rest of the ELECTRON components are hosted on the cloud. Before starting the demonstration, this is a summary of the steps that will be followed by the ELECTRON components in this scenario. Initially, the ELECTRON SDN controller and dashboard discovers the network topology, initializes the SDN switches, and scans the assets for vulnerabilities. Moreover, the ELECTRON Darcy component provides mitigation actions for assets and vulnerabilities, by using manufacturer usage description files. Starting with the scenario flow, the ELECTRON FLIDPS analyzes the Modbus network traffic, and utilizes AI-based models to detect potential threats or cyber attacks. Given a positive detection of a cyber attack, the FLIDPS generates security events, which are received by the ELECTRON Security Information and Event Management System, or CEM. The ELECTRON CEM correlates similar security events coming from the FLIDPS, and generates security alerts. Next, the ELECTRON Army component receives the security alert from the ELECTRON CEM. By utilizing information about the current topology assets from the SDN controller, and the possible mitigation actions coming from Darcy, the ELECTRON Army conducts risk assessment, and generates a risk assessment report. The risk assessment reports includes the identified threats, as well as mitigation actions that can be applied for them. Finally, the ELECTRON NERO component receives the risk assessment report and decides on the best course of action. Depending on the decisions, NERO interacts with the SDN controller and programs the network switches accordingly in order to mitigate the Modbus denial of service attack. Starting with the demonstration, this is the home page of the SDN dashboard. We observe that currently, there are 4 SDN switches available. By clicking on one of those, we can observe more information, like the SDN controller associated with that switch, the available switch ports, as well as various network statistics for each port. Next, in the topology map, we can see a depiction of all network switches and the hosts that have currently been discovered. For each host, IP and MAC addresses have been discovered. Next, in the flows page, we can see the flows that are currently installed. These flows allow normal communication between the AMR head end and the Modbus energy meters. Given the Modbus TCP attack is ongoing, FLIDPS analyzes the underlying network traffic and successfully detects the malicious network flows as Modbus DOS attack. Thus, it generates the corresponding security events, which are transmitted to the ELECTRON SIEM. We now see the dashboard of the ELECTRON SIEM, where all the security events are collected and correlated. We can navigate to the security alerts, which are raised by the ELECTRON SIEM, by correlating similar security events. By opening a security alert, we can observe information like the attacker and victim IP addresses, the associated security events, and the risk calculated by the SIEM. Moving on to the ELECTRON Army, we see that 2 risk assessment reports have already been generated. But, before that, let's have a quick look at the topology, which has been synchronized with the SDN controller. In the topology, we observe that we have collected not only the SDN switches, but also the discovered hosts. Going back to the home page, we observe that we have received threat intelligence about vulnerabilities and threats, which are coming from the ELECTRON SharePoint, the SDN controller, and open source intelligence. By inspecting the notifications, we have received a notification concerning the new alarm for the DOS threat, reported by the SIEM. This alarm has triggered multiple risk assessment tasks. Proceeding to the Risk Assessment tab, we can see all the risk assessment tasks that have been executed. By inspecting a risk assessment report, we see in the heat map that there is a single risk scenario, which corresponds to the DOS threat. Since the threat is materialized, it yields a very high probability. Moving on to the ELECTRON NERO component, we now see the terminal output of the component. We observe that we have received a new risk assessment report. As a result, and given the information provided also by ELECTRON DASI about mitigation controls, NERO has generated some mitigation actions to be applied to the SDN controller. Specifically, a flow rule has been generated, which drops the connection between the attacker and the targeted energy meter. NERO utilizes the REST API of the SDN controller in order to apply this rule. Finally, from the flows page of the SDN dashboard, we can see that the rule has been applied successfully. This indicates that the energy meter is now protected from further threats coming from the identified attacker.